me Angelina. Today's video is on solubility equilibrium.
So here's our introduction to solubility equilibrium. Let's remember about solutions and things we already know. First, a solution is a mixture of a solute and a solvent, usually one, but there could be more than one solute. Think of ocean water. There's water, salt, oxygen gas, many solutes in there. Let's talk about concentration then. There's lots of ways to express concentration. Think of ocean water again. There's many different concentrations due to so many different solutes. For example, the concentration of sodium chloride, oxygen, etc. So each solute has its own concentration, and this is a very sensitive topic and something to remember carefully. Let's look at ways to express concentration. There's molarity, which is moles solute per liter of total solution, not per liter of solvent, of course. Then we have molality. You might remember it's moles solute per kilogram of solvent. Also, think about the difference here between a kilogram of solvent and liter of total solution. Molality is often used for the physical properties because it's stable across state changes and with different temperatures. And molarity may change through states, but molality doesn't. There's also parts per million, and that's done on a particle basis, and mole fraction done on a mole basis. Let's look at some other things that we know about solutions. We know that solutions can be saturated or unsaturated or supersaturated depending on temperature. We know about the chemical properties of solutions that are based on the solvent and the solute. Also, solutions have physical properties like viscosity, freezing and boiling temperatures, density, opacity, color, conductivity, etc. So these physical properties are inherited by the solute and solvent, and not only one, it's a combination of the two of them. We also know about polar solutions, and the idea is we have non-equally charged parts of a molecule, like water. You can see here the positively charged end of the water molecule and the negatively charged end. We say this molecule has a dipole. So let's look at something that's not polar, something where all the parts are equally charged. For example, carbon tetrachloride or oils or methane are non-polar molecules. So you know that polar and non-polar molecules don't work well together. For example, they don't mix. Oil and water doesn't mix very well. And of course, you can use an emulsifier to help you to mix them. This is the like dissolves like rule. And back to an emulsifier, that's a long molecule with a polar and a non-polar end. So dissolving and dissociating are not the same thing. That we need to be reminded of. And if you can't dissolve, you can't dissociate. Some things do dissolve but don't dissociate. For example, a sugar molecule could dissolve in water but not dissociate. So for ionic compounds, we're going to say that dissolving is equal to dissociating. They're the same thing. For now, it's a fuzzy area. We're not going to go too much deeper into that. Now let's think about the process of dissolving called solvation. And to make something dissolve better, we know you can heat it up, stir it up, cut it into smaller pieces to increase the surface area. And also the nature of the solute and solvent is important. Some things are simply more readily dissolved than others. So here in this ionic compound with sodium chloride and water, water needs to pull the sodiums out of the lattice, overcome the attraction between the sodium and the chloride ions. So this is kind of a tug of war between water pulling the compound apart and the coulombic forces of attraction pulling the compound back together. That would be trying to do a precipitation reaction. That's the opposite of dissociation. So let's look at types of solutions. There's liquid solutions, aqueous solutions, and gaseous solutions. And solid solutions are alloys, for example. Stainless steel is an alloy, iron, nickel, and chromium, and carbon, and so on. But not a frozen aqueous solution. So don't get the idea that, for example, frozen salt water is not an alloy. Okay, we need concentration calculations, and we need to be well versed in these rules from last year. So there's a decent high-speed reminder about solutions and solubility. Next time we'll look at separating solutions of ions by precipitation, and after that, solubility calculations and KSP. So thanks everyone. Stay tuned, it's high speed. We'll see you soon. Have a look at the next 2 videos in this playlist for more, and stay tuned for our next lesson, lesson 13, separating solutions.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe.
Hey guys, it's me Angelina. Today's video is solubility. Sorry. Hey guys, it's me Angelina. Today's video is